for official purpose. Okay, I like to wish everyone a happy and prosperous new year. So, I am Sofen Kumar Jana. Currently, I am working as a CFD analyst in Oracle Corporation, Pune. So, today I am going to present a topic on radiative heat transfer and challenge for engineers. It seems like a technical thing, but believe me, it is something. Last session I have in the minutes I joined in the last session. It was really about motivation. So I got an email few days back from the authorities of state that I need to be motivate the students. Then I said, what else can be a big motivation than science and technology itself? So believe me, this is Yajum. I congratulate you all of you first for getting admission into this prestigious institution. You all have gone through rigorous test and all this exam procedure to get seat in the this prestigious institution. For that, I like to congratulate you. This session, as far as concerned, I keep it multidisciplinary. So keeping all those things in mind that students from different batch they are joining, students having different educational background they are also joining. So the prerequisite again every technical session is a prerequisite. The prerequisite for this session is your plus two level of physics and mathematics knowledge. Maybe if someone gone through that SC Burma book, so that is sufficient because normally I teach the PG and PhD students, so that's why I put a lot of mathematics. But when this request came, I was really happy that I am interacting with the first year UG students, and I try to minimize any mathematical things with picture, with graph. Next 1 hour, I am going to take a journey to a different path where engineering, how the subject itself developed, the radiation, and what is the challenge for engineer. So this thing. So hope everyone will enjoy. And in between, if you have any doubts, please ask me in the chat, or you can directly ask me a voice. We can stop and discuss. We can further process. I think we have an interaction session at the end. So to be honest, I am not a traditional motivational speaker like Chetan Bhagat or Maheshwari, those people. But again, I'll try to motivate you something towards the science. It's a passion that will I will generate you within you so that you will follow the science. You will enjoy what you are reading. You will enjoy what you are doing. So can I start, sir? It's already 5 o'clock. Can we start the topic?
Yes, sir. We can start.
Okay, I'm sharing the full screen mode there. Okay, so welcome all of you to this session, radiative heat transfer and challenges for engineer. So in the cover slide itself, you can see there is a lady who is suffering from fever, and there is a doctor is there. So normally when we are suffering with fever, what we are doing? So we put a thermometer to measure what is the temperature. But fortunately or unfortunately, the cartoonist made the doctor is Dr. Planck. It's Dr. Max Planck, and he is telling he don't need a thermometer to measure the temperature because the glow of his face is telling that something is running out of high fever. Again, this subject of radiation, it's a very interesting and it's a very well-developed subject. At the same time, there is a question, it's a radiation area. Once you are coming into this subject, means you are in a trap. So the kind of anxiety, the kind of interest you get in this subject, you forget everything. You start looking at it. But again, this is a caution notice. So maintain a balance because this subject is quite interesting. So let me come to the thing. So this book, okay. Okay. Okay, so let me come to the topic. So let's start by I'm going to the medieval time. So this lecture, I promise, I will keep the mathematics part minimized. I will explain all those things what you have learned in your 12th class. But again, this is a rigorous and simplistic definition of that that will make your conduct clear. And I hope this thing will helpful for you in your branch or in the higher study when you are going for a job. Every time you face the situation, you will really enjoy the what you have done through today. So I am going to the medieval history before. It's a very nice idea to start the session with some. So medieval age, named Perry. So he gave the atomic theory of matter. What is this atomic theory? Before Perry ascended, there was the Aristotelian dogma. So what it means, the science, development, the philosophy, everything was dominated by Aristotelian thought. What Aristotelian thought was? Aristotelian thought was that the universe is entirely composed of matter, right? Then around mid of 15th century, so this Perry ascending, he little bit deviate, come out of that thought, Aristotelian dogma. He then prescribed few things because that time science was started developing. At the same time, church society predominant role. They put Galileo in, inventory scientific and which is against the policy of the church. So I am a big fan of this man, Bertrand Russell. In fact, he is a mathematician and he got a Nobel Prize for the literature. So in his book, he has explained very nicely how this development in science happened in Europe, especially from the medieval era to from the Socrates era to medieval era to modern era. So he has explained. So from there I am telling. So Gassendi thought that the entire universe is not only composed of atom, there is some fact universe is composed of atom, and there is some fraction there is nothing. If there is absence of atom, he named it as what? He named it as void, right? So and what he assumed that God exists definitely, otherwise the church society will finite number of individual atoms. Then God has counting divine relationship to a creation of matter. Human have free will, human have soul exists, and God has not born and will never die. Right? So again, from all this his theory, only thing is which is interest that universe is not only composed of matter, there is some matter and some void, and atom is the smallest unit of that matter, which is further indivisible. So this is Perry Gassendi. So after his Perry Gassendi, there is started the era of René Descartes. This is the French mathematician after whom the Cartesian geometry came, and the famous British mathematician and the physicist Sir Isaac Newton. So what they did, because all of you know a lot about Newton, you have studied in your plus two books, from the 10 books, he has did a lot of things in physics, most of classical physics, almost is the father of classical physics. So when he came to the optics part, then Newton postulated theory. Then that point it is not clear. You have, I assume that every one of you have done this refraction, all this experiment in the laboratory. All of you know what this reflection refraction phenomenon. Similarly, those time also in 15th century, 16th century, people also aware about those things. Okay, and most of the science that came to existence through observation. So from the observation, Newton then prescribed the corpuscular theory of light. It was first by René Descartes, then Newton carried forward the theory further to explain the phenomena, reflection, refraction, all those phenomena. According to the corpuscular theory of light, what is the entire thing, light, they're composed of some particle, named it somewhere ether particle, right? So through that ether, the particle they started moving. They assume it's a light is a particle in nature, right? The corpuscular started in 1637 and it was carried forward by Newton around 1673. He explained the things. But the problem with this theory, other branch of Newtonian mechanics, motion, kinematics, everything they work fine. The problem with this light in 15th century is that with this particle nature, most of the phenomena is very difficult to describe, right? Reflection, refraction, and there are the other phenomena I am explaining that is the diffraction phenomena that are very difficult to describe within this corpuscular or particle nature of the light, right? So what this phenomena is telling, so I am explaining you the whole experiment. There are the cardboard is there. There is a thin narrow gap is in the cardboard. So what will happen? A coherent source of light is coming. Here a beam of light is coming. They are passing through the narrow gap, right? Once they are passing through the narrow gap, they are propagating, right? Then after a certain distance, they are measuring the intensity of light. Okay, but the process of measuring, yes. Everything all right? Hello? Hello?
Yes, sir.
Everything all right? We'll continue or some I had some questions.
Yes, sir. Continue.
Okay, then in the process of measuring this diffraction, what if they found? They found there is a certain band of dark and light, dark and light, dark and light. Continuously, there are certain bands are formed in the spotter, dark spotter form. Then this particle nature of the light was failed to explain this diffraction phenomenon, because how a light plus light can form a dark? We are pushing a light over there and a dark light that continuously. How it is possible? Light plus light is fully dark. Are you cheating me? Right? Then what happened? This particle nature of the light that failed to explain phenomena of or the light. Right? Then it has continued from the Newtonian era to 18th century, 19th century. People have tried a lot in their endeavor to develop some theory that can explain what is light actually there, right? What is light that can be explained. So it is around the early of 19th century, right? It is a Lord Kelvin, Thomas Barrow, right? He developed published a paper in Royal Institution of Great Britain. Okay, what is the title of paper? 19th century clouds over dynamical theory of heat and light. Okay, so this clouds what he referred is not about Amazon cloud or the Netflix cloud. The cloud he was referring was the black body spectrum and the Michelson and Morley experiment, right? I will explain bit by bit. The next slide, what is black body spectrum, what is Michelson and Morley experiment, right? So what Lord Kelvin present that dramatically changed the research of the phenomena in 19th century and 20th century. Okay, because of these two paper. After that, there is a birth of quantum mechanics, there is a birth of modern physics, there is a birth of relativity, everything came into existence. So this is the point where they are starting growing. The science was growing in a rapid speed. So Lord Kelvin in the Royal Institution of Great Britain, these two paper about the Michelson and Morley experiment and the black body experiment. What Michelson and Morley did, this is a cartoon, they are not actually Michelson and Morley, but this experiment is a famous experiment. If you Google it, if you find it any interesting scientific literature, you will find to find the ether particle. As I told, the Newtonian time they assume that there is some medium that is called ether, through which there is a massless point particle through which light is propagating. To find the presence of ether, this Michelson and Morley they did the experiment. Okay, so what they did in the experiment? They did the experiment in the summer. They did the experiment. They did the experiment in the extreme time when temperature was high. They did the experiment in time when there is just snowfall. They did it in the riverside. They did it in the top of the mountain. They did it in the ocean. Everywhere they did it to find if there is an ether or not. Finally, they did not find any existence of the ether. Okay, then they postulated the theory. So I am not going to mathematical part of the theory, but this theory substantially changed the physics at that point of time. Still, the experimental setup is there in the Western Reserve University at Cleveland, Ohio, right? So this was the cloud that was Thomas Barrow and Lord Kelvin was referring to here. That is the Michelson and Morley experiment. This deep part of the concept of relativity. Then there is a clear that there is no such things like ether exist as Newton or Descartes prescribed a long back. So from the atomistic theory to the Newton corpuscle theory, the difference is that in atomistic theory, they assume that atom is the last form of the matter which cannot be further divisible. But here in the corpuscular theory, they assume the corpuscle is not the final form, it is still divisible. Then chronologically, when they reach at the Michelson-Morley experiment, they completely discard the presence of any such particle, right? Then let's start what is light, right? So what is light? Most of the science they developed through the astronomy or through the observation, because people used to be passionate astronomer in this medieval age. There are some astronomer William Herschel. He did a very simple but very interesting phenomenon. In fact, the man he discovered the planet Uranus. What he did, he put some tiles of thermometer behind the prism. What will happen once light will hit the prism? They will split. Then he found the temperature in the thermometer. There is a rise in temperature of the thermometer, right? Then before that, there was not any clean distinction between light and heat. If you go to the Newton has different heat, there is a different law for optics, but there is not any coincidence between light and heat. But this Herschel, the thing started telling that this light is nothing but this is a form of heat, because once you put they're going to increase the temperature, but again, this heat is coming in certain band or certain frequency. We will see subsequently what exactly he is telling. But by this time, after herself, it was clear that light is nothing but a form of heat, or heat is nothing but a form of light, right? So then let's come. What is the spectrum I told you? Okay. So then it is Kirchhoff, right? All of you have studied the Kirchhoff law during your JE or your plus two. So this is a man, famous German man, Kirchhoff, who gave the concept of black body, right? What is this black body? Possibly it is the proper time to explore what is the purpose of the black body, if there is some ideal black body exist or not. To be honest, there is not any ideal black body exist in this universe. What is the black body? Then Kirchhoff assume this black body is an ideal body, material stuff that absorbs all radiation. If I put any radiation, it will absorb. Then it will emit all the radiation at all possible wavelengths. Then this is the assumption of Kirchhoff. There is not any reality, right? Then Kirchhoff further found when such material black body heated, then it emits radiation at all wavelengths. Okay? We'll come to the concept what is all wavelengths, right? Black body is a perfect emitter and absorber of radiation, because every radiation I put on the black body, it emits, it absorbs, then subsequently once it is heated, it is emitting, right? For an arbitrary body, emitting, absorbing thermal radiation in thermodynamics equilibrium means the temperature is not increasing, it's a constant temperature, it is absorbing, emitting, the emissivity equals to the absorptivity, as long as it is in thermal equilibrium with the surrounding, right? So let's see the thing, what is all wavelength. If you go and compare the wavelength range, here the wavelength range is ranging from the gamma ray to radio wave. Okay, the gamma ray, if you look, something around the wavelength range 10 to the minus 12 meter, while the radio wave, that is quite big, it is the size of a tall building, you can see it 10 to the 3 meter, that is the wavelength, and the frequency, where the gamma ray frequency is in 10 to the 20 hertz. Okay, then the radio wave has a frequency of 10 to the 4 hertz. If you put this on a graph paper, you see a very huge spectrum. Possibly you have to take the logarithmic of the axis to plot this value if you measure something in this range. That's why they take all the wavelengths from the 0 to infinite, those range, because 10 to the power minus 12 is something close to 0, right? Compared to 10 to the power 0 to 10 to the power 3 is 1000, it's a quite big length, right? So that's why in the radiation literature, wavelength from 0 to infinite, they have put it. This is the meaning. Okay, something we are going gamma ray, it is a class of atomic nuclei to a very tall building. You can say a Burj Khalifa kind of building. That order of magnitude, this radiation wavelength varies. Right? It is clear. Then teacher gave the concept of the black body. Okay, then we are now clear about the black body. Then see what happens next. Then Kirchhoff assumed it's a black body. Kirchhoff did not materialize what is black body. Then it was another two German students, Wien and Leumann, who formalized the concept of black body. Okay, what they did for the convenience, they put a very simplistic sphere having very tiny holes at the top, and through the tiny holes, light is getting into the enclosure. Once it's getting into the enclosure, it is passing through infinite number of reflection. It cannot get out of the enclosure. In that case, what will happen? You put a source that is getting completely absorbed, okay, inside the body. Fraction will be absorbed, some fraction will be reflected, then again during the successive collision with the boundary, almost all the light will be absorbed, right? So for the realization, Wien and Leumann, they give this kind of concept, what is the black body, right? Black body, they propose a hollow sphere, okay, at having a smaller aperture, then through that they put the light and they measure the black body radiation. So normally the radiation is measured by a device called bolometer, thermopile, or radiometer. Right? Then it was Dulong and Petit. In chemistry, all of us read this Dulong and Petit's law. So let me explain what this Dulong and Petit did. They definitely were the material scientists. They did a lot of chemistry side. But even if for their purpose, what they did a lot of research on the radiation itself to prepare the material. Okay. So they have taken a spherical geometry, just as it's a spherical cavity. In the center, they put a sphere, right? So what they did, they heated the sphere. What will happen? As the sphere is heated, they'll start emitting radiation towards the periphery, and those radiation will come. This radiation will strike the cavity, and what will do? They will be absorbed by the cavity. Okay. So what they do, Dulong and Petit, they did the experiment for a quite different number of cases. Okay. They heated to different temperature. Gradually what they did, they started increasing the pressure, because again it is heated, there is some stream of thing, because of the buoyancy effect they started moving, they heat over here. To eliminate those effects, they started eliminate the molecules such that there is a convection is completely stopped in the region, and there is only heat transfer from here to in the frozen state, right? They extrapolate those regions. That's why they call it a zero pressure. Zero pressure means there is no molecular movement is occurring, but still the right, they extrapolated the zero pressure, assuming there is a radiation exists. So this is from that experiment they give some theory for radiation, how the radiation propagates to the temperature, because now they found that radiation is nothing but a light in the form of heat. So this is the formal mathematical definition Dulong and Petit try to give in terms of how the radiation and heat they are behave. So from their experiment they gave it, but although it is not a correct form, but they started an early attempt to present the theory. But again, after the 7 decades of the Dulong and Petit experiment, there was a famous man, Austrian physicist, Joseph Stefan. Okay, he gave access, re-access all the data of Dulong, Petit, then try playing with those mathematical data. By playing such mathematical data, he gave the concept that energy, if you heat it to body temperature T, the energy it emits is equal to sigma into its absolute, is directly proportional to the fourth power of its absolute temperature. Any body, if you are heated, the amount of energy to radiate directly proportional to the fourth power of its absolute temperature. And he naturally puts a proportionality constant sigma, right? This is exactly what he did. He just reaccessed the experiment that did by the Dulong and Petit that did it. And what is his argument regarding the why Dulong and Petit experiment was wrong? He told even if you freeze the molecular motion, but there is a conduction will be there. The molecule may not move from here to here. If a molecule in the media, they move this region to this region and exchange the heat, then it is called convection. But even if the molecule is not moving, by collision it is exchanging energy to next molecule to next molecule. That mechanism also it is coming, that is called conduction. Then the Stefan argued the experiment done by Dulong and Petit, that might be possibility radiation is going, heat is also going in the conduction mechanism as well as radiation mechanism. You cannot completely claim that even if you are making it as a zero pressure, there is a completely radiation, because molecular conduction will be there. So by playing with all mathematics, I am not going to derive whole mathematics over here. So he came with the formula. This is a famous formula. Even this is today is correct and largely used, that epsilon equal to sigma T to the power 4. This is how the radiation came. But again, what is the value of sigma? There is nothing. This is a proportionality constant. Then it was Stefan's successor, right? 3 German genius mathematicians, Leumer, Finstream, and Colburn. Okay, they did a lot of experiments with the Stefan's. Then they finally found the Stefan's constant value 5.67 10 to the minus 8 watt per meter square for Kelvin to the power minus 4. So this constant definitely all of you have used in your 12th physics and all of you are aware, but may not be aware how this came. They did all the experiment, how they assessed, the astronomers already did the data, as I already told. All the medieval science they developed through astronomy or by observing the universe, because there is not a what scientist, either they were natural philosopher or professor, right? All the scientists. So all the natural philosophers, they used to observe something, they used to find some data, generate some theory out of this, like Newton, Descartes, they did it. Okay, so they access some data that is from the astronomer. They found that from this astronomer have already that point data, that what is the diameter of the sun, what is the then from that what is the sun temperature. They found that the Earth's surface, the heat flux because of the radiation, that is how much? 1360 watt per square meter, right? This amount of heat is coming to the Earth's surface from sun. This amount of radiation heat flux is coming, right? Second, Then Stefan himself, before this successor Lumar or Princeton, the Stefan himself calculated what? The sun's temperature. It is around 6000 degree Kelvin. The sun's surface temperature. He calculated using his formula of radiation, Stefan, right? Further using the same law, Earth and sun temperature. The sun temperature is known. Then the radiation law is known. He calculated what? The temperature of the earth is around minus 18 degrees centigrade. This maybe seems like quite unnatural. We are in a situation now 20 degrees, where is minus 80 degree, maybe some part of Russia, some part of Europe, not in other part. But again, what he found, it is just above the earth atmosphere, few kilometers from the ground, because there itself radiation is coming, and what is happening in the our level, in the ground level, that there are a lot of other local phenomena is there. We have a vehicle, we are burning the thing, there is a greenhouse, a lot of things that locally control the thing. But because of the sun's radiation, the temperature is now, it's around 18 degrees centigrade, which is a quite realistic temperature just above the surface of the atmosphere, right? Few kilometers away from the thing. Even if you fly in an aeroplane to some international flight and all, you can see the temperature it is showing the recording, which is close to minus 10, minus 12, minus 18 degrees centigrade. So those days, with not lot of access to computer, digital things, internet, through a lot of observation and experiment, they found it the fact that minus 18 degrees centigrade is the temperature to the Earth atmosphere, even if satellites were not there at that time. That's why genius is genius. The Joseph Stefan was a genius, and all his successors, Luma, Princeton, and Colburn, they are also. So now, repeated what I am going to use in the radiation. This is the radiation literature has repeated what on a spectrum. Okay, you might have heard something spectrum, right? What is spectrum? This is a mathematical one. So for the simplifying thing, I am coming here to explain. Okay. Okay. So what is spectrum actually, right? So let's see what is the spectrum. To understand every physics, again we have to go to the nature. We have to closely observe the nature. What is it? You see, the swan is swimming, right? The baby swans are swimming. So each swan, during tapping up their feather, they generate some wave, right? Just below the swan, you can see some simple wave is generating, right? Those simple wave, another swan is generating another wave. When these two waves then intermix with each other, they form a complex nature of the wave, right? Similarly, the spectrum is nothing but every complex thing they composed of some simple thing, right? Just like you see, this is a sine wave. Okay, this has some frequency 2 pi. This is a sine wave. This is the frequency having 4 pi. This is the sine wave. This is minus 2 pi to 2 pi. I have this is a number of cycle you can calculate. You can find the frequency. There are simple sine wave of 3 different frequencies. Once I take them, add them, there is a different shape of the wave. Can you find out it is a sine wave? It's a very complex wave. You cannot distinguish. But if you look, you will find a very beautiful sine wave is the elemental constituent. So that's the word the spectrum comes. Spectrum means the simple fundamental constituent of the signal or the function, that is called the spectrum. So in the light, we have already described the different frequency. The waves are coming. We have already saw what is the frequency range from the radio wave to the gamma wave range, right? So each frequency may have some simple structure that casually coming. So that's the word often they use as a spectrum. Okay. So once you put the white light, over the prism, they split into different parts, right? So red, orange, you have seen it from the childhood school. They call it spectrum. The spectrum is nothing. It is a collection of different wavelengths. Similarly, the matter is composed of how much of fundamental unit. So the all collection of all such fundamental unit is called spectrum. Clear? So this is a simple example I did it. So once you are in the highest semester, learn Fourier analysis and all, then you will be clear about the spectrum and things. To ask your math teacher a lot of questions that what is spectrum, clearly gives some physical insight. This will give you a lot of physical reality, physical insight. Okay. So then, after the discovery of the radiation by the Luma, Princeton, and Colburn, then people started learning the black body spectrum. Right? What is black body? Black body concept was given by Kirchhoff. Right? Then it was shape of the black body was given by Wayne and Luma. The same Luma gave the Stefan's law, the radiation formula they gave from the Stefan, Luma, Princeton. Then they started studying the black body spectrum. Means they heated a black body to certain temperature, and once the black body is heated, they started to emitting energy. The energy is emitted over all wavelengths because the heat is going right from the surface. Now heat and radiation, they are the light and heat, they are the same things. They are different form and different values they are coming associated. So they measure the energy density, okay, for wavelength. Okay, once you hit it, the light is going. Once you hit at the surface, it has radiation. The radiation happened in all possible temperature for each wavelength range. They measure how much of energy it is carrying and they plotted the graph. Right. The graph is looks something like this. Right. This is my wavelength along the x-axis, my energy versus the y-axis. There something graph comes like this. So what they notice, for a particular wavelength, the radiation energy is high. Okay, for a particular wavelength here, for this 5500 Kelvin, for a particular wavelength corresponding to this, the energy is high, right? Similarly, for this there is a particular wavelength. So either side of the wavelength, the energy carried by the thing that goes on decreasing, right? So for the increasing the temperature, shifting of the wavelength associated with the high energy transfer. Suppose at 3500 or Kelvin, this is the wavelength which is associated with the highest energy transfer, right? If you can see over the 4500, this wavelength shift from this side. This is reducing, right? This is called black body spectrum, right? They give the visible spectrum around 400 to 700 nanometer. This is the visible spectrum. So similarly, there is other spectrum also in the light, that the black body spectrum. So by these things, they form a spectral band. I already explained you what is the spectrum, so don't be confused. They form a spectral band. The spectral band is not a all collection of all possible wavelengths. They are associated with light. So this spectral band, they found it something order of, as I tell, 10 to the minus 5 to 10 to the power 4, that range of wavelength, right? Anything that is very less subatomic level, that is called gamma ray. Little bit higher, that is called X-ray. Then there is a ultraviolet. Then there is a nanometer range. There is a visible wavelength. Then above the visible, there is an infrared wavelength, and there is a region called microwave range. And most of the engineer, we are interested mostly in this infrared and thermal radiation visible range, because most of the phenomena in optics, most of the phenomena in our appliance design, so they are based on this thermal radiation. We are looking for the radiation which is associated with the heat transfer. Sorry, can you mute some noise I am seeing from the other side? Any question? Okay, let's proceed. So now it is clear about what is the spectral band. The spectral band is nothing but all collection of all possible wavelengths associated with the radiation. Then the spectral band, then subdivided into different categories, gamma, thermal radiation, infrared, microwave, like that, right? So then there is another student, that is Ludwig Boltzmann. He is another genius who is the father of statistical mechanics. He came with an analogy with photon Carnot engine. All of you might have studied about the Carnot engine, ideal heat Carnot engine, you have studied in physics. So this Boltzmann, he came with the concept of ideal Carnot engine to find out further develop the theory. What is that Carnot engine theory? There is a Carnot engine cylinder piston arrangement. You have already studied in the philosophy level, right? Normally what will happen? The gas in the piston expands, they are compressed, then they extract the heat from the source, then reject heat in the sink. Like that, the Carnot engine operates. So what Boltzmann said, he has taken a photon Carnot engine. Then he assumes there is not any matter inside it, right? It's a vacuum, right? Then this vacuum has, instead of the gas, there is some particles are there that he called photon, right? Then we name the engine as photon Carnot engine. Because of the photon, they are receiving the heat from the sink. What will happen? The photon will receive the heat, they will strike with the piston, then the piston will move towards the top, right? Similarly, while the rejecting the photons, the piston will come back. Right? Then the material object, the conventional Carnot engine, is replaced by the photon in this photon Carnot engine. Radiation flux imports mechanical pressure in the striking object, because normally in the air, it is a molecule, air molecule, that exert the pressure on the piston that moves the piston. Here the thing is a radiation force that is driving this Carnot engine, right? The engine are completely operated by radiation pressure. There is not any mechanical pressure, means there is not any molecular pressure, right? Walls of the cylinder are perfectly reflected in nature. These two walls, they are perfectly reflecting. They don't absorb anything, right? Source and sinks. From the analogy, what he found, pressure equals to radiative flux by c, where c is the velocity of the light. So this is from the dimensional ground, you can check it. It is very mathematical derived analysis I did in the first chapter of your plus 2, dimensional consistency, right? So even if someone will confuse whether what is the radiation pressure, whether I put a laser light on you, I will put a light on you, I am giving them force, but again you cannot feel it. Why? The radiative flux for the in the daytime is around 300 watt per meter square, produces the amount of radiation flux. If you whole day start on the sun, under the sun, or play cricket in the field, you will get a pressure on you, radiation, because of the radiation that is order of 10 to the 9. While the atmospheric pressure is around 10 to the power 11 times, which is small than 10 to the power 11 times less than the atmospheric pressure. Atmospheric pressure is some bar is in the order of 10 to the power 5, right? Here is 10 to the power minus 6, right? Then what will happen? 10 to the power 11 times less the radiation pressure. That's why while you are in the light or you are in a sunny day playing football, you do not feel an extra pressure over you because it's a very negligible, but still the radiation gives some pressure. That's what the Boltzmann considered for his photon converting. Okay. Then he analyzed that time the Maxwell's model for kinetic theory of gas was highly established. Then he did some analogy with the kinetic theory of the gases, diatomic gases and photon. Then pressure is equal to how much? 1 by 3 mn v square or c square root mean square velocity, right? This is what the kinetic theory of gas is telling, Maxwell theory. Similarly, he thought the photon, he did some lot of mathematics. I am not going to do those mathematics because mathematics are make the people scary. I don't want to make you unhappy with a lot of mathematics derivation. But again, by doing that, what interesting thing he found out, just like thermodynamics, we have Cp, Cv, R value, universal gas constant, specific heat constant, all. H equal to, so okay. So then it will come later. Right? The astronomical data, they found the value of Stephen's thing, this Newmark, Princeton, and Colburn. Theoretically, by taking the photon Carnot engine, he derived all such physics, they don't always come from rigorous mathematical derivation rather than from the observation. Before Boltzmann, three people over here, they analyzed the astronomical to honor both the things. But unfortunately, the thing with the Stephen, by deriving mathematics and all those things, he went into depression and committed suicide. That's what. And physics. Okay. Discovery of radiation is this Well's law, right? William Werner Weiss, this is another German mathematician. He did another fantastic experiment. All of you have read about the Doppler effect, the train is coming, the source, observer, all those things in mechanics. The source is moving towards observer, the observer is moving towards source. They both are moving. Okay. Then finally, the Doppler effect is showing the what is his experiment, Wein's experiment. I am explaining. Once experiment is there is a tiny source is over there, right? They are emitting radiation because radiation there is a fixed expanding in nature, right? Adiabatic chamber is there, okay, and the chamber walls are expanding. Means chamber you can assume it's a fixed balloon as if in the radiation pressure. Normally the balloons blows in the atomic pressure. Even if there is a fixed balloon, right, you can give the radiation pressure. Under the radiation pressure, the balloon itself is now growing, right? He assumed the while assumed that the emitted wavelengths are getting Doppler shift. There is again Doppler formula you have studied. I am not going to explain what is the Doppler formula. Here, which is emitted frequency that is also moving, right? It is not a stationary observer or stationary source, right? Then by doing so, this is the Doppler formula. This R is the relative velocity. Relative velocity, which is this membrane is moving. This plus minus sign where the source is moving towards the observer is moving towards source. That with doing that, he gives this formula where C stands for velocity of the light. F stands for observed frequency. Someone suppose stands at this plane, what frequency he will observe equals to what frequency it is when did it, right? So by doing so, he again comes. Earlier people have skipped the notice the blackbody thing. Then by doing so, what he give Wien's displacement law. What he displaced earlier we have noticed as you go on increasing the temperature, the peak temperature which is associated with the maximum energy force that is getting shift towards the left side of the axis, right? So how much of shift, whether there is any relation because here the maximum temperature or maximum wavelength is here which is associated with temperature of 3500. That is shifted to this amount while I'm coming at temperature 5500. So then from his experiment, okay, then he gave a formula. This maximum temperature times the peak wavelength that is associated with the maximum wavelength that is associated with the wavelength associated with the maximum heat transfer into product of the corresponding temperature. They are a constant. That is called Wien's constant. From his experiment, he find out the value of the constant, right? Then this law is well agreed with the experiment with Lima in his edition what he did it. Okay. Then for this discovery, he got the Nobel Prize in 1911. Right? Application. What is the application? This discovery as a phenomenal application. Right? That time, then this discovery of weight was used to design a tungsten lamp, which is heated up to 2000 Kelvin and emitted 1.555 thing. Then once a blanket of water vapor absorbs electromagnetic radiation more than 10 microns, then it is creating a temperature of 27 degrees centigrade. Earlier we have seen while Stephan calculated the temperature we find on the Earth surface is negative something, right? Then Earth has the atmosphere. Atmosphere is not only composed of the ideal gas, they are composed of some carbon dioxide, carbon monoxide, water vapor and all. Those particles absorb some radiation, right? Again, because of those things, because from the Wien's displacement formula, we find that the temperature is around 27 degrees, which is quite normal temperature in the month of February, Bhubaneswar, October, November, February, Bhubaneswar. This is the temperature we got the Wien's displacement. Sorry, some noise from the other side. Can you please mute? Okay. Then Wien is also the first one who describes the microscopic function of the radiation. Okay, taking the statistical mechanics of the Boltzmann, Wien discovered the statistical law. Okay, so I am not going to detail into the mathematical part for which he got the Nobel Prize. So then after the thing, Wien, there is a two genius mathematicians, British mathematics. They call Rayleigh and Jeans. Can you please mute your microphone? It is noisy here. There are some genes. Okay. They did some experiment because what was the problem with one formula? This formula was well predicted at lower wavelength range. Okay. Then it is called Rayleigh jeans. Rayleigh jeans derives self-constant classical microscopic picture of the blackbody radiation. They consider blackbody radiation inside a confined cavity. they derive some formula about black body radiation, Rayleigh engines. So by what they consider just like a simple vibration. This vibration equation they are considered first harmonic vibration. They are considered with detailed mathematical analogy. They give some experiments regarding the wavelength and energy relation, right? So they give something. You can see the temperature and wavelength relation, the corresponding to energy. They give some temperature and energy relation. Rayleigh. I am not going to mathematics detail here. Why is the thing? But what was the problem with this? Why did Rayleigh did? What was the problem with it? Okay. Then the 50th century mathematics they started with birth of quantum mechanics. Can you please mute the mic? I am getting the disturbance over you. Sir, can you help me to mute?
Can you mute all guys? Can you mute please? Tanmay? Can you mute?
Can you please? Is everything okay, sir? Can we proceed right now?
Yes, sir. Yes, sir. We can proceed.
Okay. Then it was a Max Planck, right? What is the need of another thing? Quantum mechanics is very difficult and unjustified to describe that quantum mechanics in a single slide. But I am giving you the idea. What is the black body part Wien did? That was Wien's law that is applicable to this side. Rayleigh's law that is applicable to the other side of the black body radiation. Okay, and both law are failing near the central region, right? There was need of a theory, right, which will integrate all the things and completely explain the black body radiation. That's why this was done by a genius German mathematician named Max Planck, and then the things Planck's quantum mechanics came into existence, right? Then two formula was heavy because I don't know, I am doing the experiment which to use, either Rayleigh to use or the Wien's to use, right? Then people started complaining these things are not matching the intermediate region. Then he did this. Then the next formula was developed by this genius mathematician named this Max Planck. Planck. Okay. Finally, in 1901, Max Planck published his work on quantum statics, assuming that molecules can emit photons at distinct energy levels. He found the spectral blackbody emissive power distribution, now commonly known as Planck's law. We'll come, that is Planck's law next slide. Sunday evening, he sent this formula with a postcard to his friend Ruben. Then he published his work in some, Ruben informed him from the experiment. His friend Ruben confirmed that derivation, mathematical derivation with the experimental thing. Then he presented the result in the Physical Society meeting and published his analog theories. This is how the quantum mechanics got back at the 19th century, right? Planck gives some extraordinary effort to find out E is equal to h nu, the amount of energy that is coming from a substance that is equals to E equal to h nu. But h is a Planck's constant that he modified Planck's constant that he calculated based on the not a mathematical derivation in the quantum mechanics. It is beyond the purview at this present lecture to go and derive every detail of quantum. But the biggest finding is that he found something on the Planck's law, right? So now from the Planck's law, I am escaping the detailed mathematical thing. So the ideal finding, this Planck's law perfectly explains all the black body radiation at all temperatures. That is the beauty of this Planck's quantum mechanics, right? So then Planck's law, this all genius came with the further genius, right? This Planck's quantum mechanics, this was the pioneer, gives back to substantially many fields in physics there, like relativity, photoelectric effect. Subsequently, Einstein has he was not accepting Planck's quantum theory. He subsequently based on photoelectric effect and got a Nobel Prize. Planck got a Nobel Prize in 1918, and I guess Einstein got it in 1923, right? Finally, Einstein used his Planck's quantum theory to his derivation of photoelectric effect, right? So these are all genius plants. Again, give some zero energy point, which is of course interesting thing. But again, mathematics are escaping. It's not okay to go the mathematics. But again, one important thing I can see the zero energy. Some American scientist Mulligan later research and confirm it. This is a kind of energy. If you have a half cup of zero energy, right? 0 point energy, that is sufficient enough for the entire ocean in the planet. If a half cup of zero energy has that much of 0 point energy, if composed of that much of capacity, it can boil the entire ocean, right? But again, there is a debate. Einstein told our universe is such a big that that much of energy, even if you have half cup energy, with the that telling that it will get the total boil the total ocean, right? So then this is all the thing how the radiation from the minimal observation to atomic theory to the Planck's modern quantum theory come into existence. Then now the theory, what is the role for engineering? You can see in the galaxy of Nobel laureate, all people, contemporary people, Max Planck, Millikan, North, everyone got all. For an engineer, as for us, what matter is that thermal radiation, right? Because any of we do engineer, like suppose a chemical engineer, I am doing the furnace, then I am intended to thermal radiation. I am doing some blast furnace work, and a mechanical engineer I am doing. I am also using thermal radiation. As an electrical engineer, working with the transformer, it is heating. That's why also thermal radiation. As an electronics engineer, we are doing some signal processing device that is heating. That is thermal engineer, thermal radiation phenomena. So everyone, our point of interest is not beyond this ultraviolet gamma ray, because physics is really care what is happening in the X-ray gamma ray region. There is some other astrophysicists they are interested into this radio wave region. For an engineer, the interest region is a thermal radiation region, right? Based on this thermal radiation region, we have a lot of challenges. In next two slides, I will show what is the challenges. Already in the furnace, as an engineer, you join industry, right? Some blast. Suppose challenge for you to design a furnace that will optimize melting of your aluminium. You have to design the furnace. So you have to consider all these thermal radiation parameters because of the radiation, what is the temperature is reaching over there, and whether the temperature is more than aluminium melting temperature is or not. Lot of things. Similarly, design so that if you have burger or pizza, air conditioner or inverter, anything that has through radiation heat exchange. Similarly, if your laptop or the smartphone, anything, you have an electronic component which consumes energy heated. Sometimes your smartphone heated a lot. You need some chip cooling or smartphone cooling technology. Right? So what is happening over there? The thermal radiation is the plays a substantial role to design this device, to operate this device. Having a this device, you need to understand the radiation. But directly or indirectly, may work on radiation or not, that's a different thing, directly. But indirectly, you have to understand that is thermal radiation is a significant effect. Right? Even if you have time, you need to put down the microprocessor, otherwise the radiation, because of the radiation temperature is high, all the electronics component will melt down. Similarly, if you come to the medical thing, nowadays if you go for laser dental surgery, if you go for laser corona surgery, all those things are full of radiation. So few years back, I made an Indian professor, Indian origin, American professor in USA. So Professor Kunal Mitra. Okay, they were in the process of designing a laser, which again worked on the principle that for some femtosecond is the 10⁻⁻14 of a second, that laser will trigger for that much of time, and the amount of thermal energy it carries, that will go. Suppose you have a tumor, without surgery, how to remove the tumor? They will move the laser. Okay. That laser has the order tensor minus 30. Then directly that laser will go to the tumor. It will on the tumor. Okay. If the second order there is a deviation in the laser, that may be burned when. So you can imagine how people are working in this radiation to develop such equipment which is working for femtosecond and doing the radiation surgery. Again, for the space vehicle, again in the combustion chamber, please mute. I am getting a lot of okay, so combustion chamber from the space vehicle, everywhere they are getting encountered with the radiation, right? So then, what is the challenge? Next challenge for engineer, okay? So to do this radiation, whether you are electronics engineer, you are electrical engineer, you are a mechanical engineer, you are an aerospace engineer. Normally, this topic radiation heat transfer, they are taught in the branch of mechanical and aerospace engineering. But it has application. I have seen electronics people in my present company. They come to us for a chip design. Okay, the normally every during chip design they emit heat and all, so that there will be specified temperature is maintained in the cabinet chamber. How we do it? We do by considering the thermal radiation, what is the heat transfer, whether by thermal radiation the chip temperature is exceeding certain threshold temperature or not, if it is exceeding whether the semiconductor is work in those region or not. We do this kind of simulation in the industry. Being in the industry, we work for the electronics people. Being electronics people, although they don't directly work in the radiation, they need to understand radiation. Okay, because of the radiation, my component temperature is increasing, so I need to minimize the radiation parameter over, right? So that's why what I today thought is may not be completely applicable to the branch. You can directly go and started doing some research about the thing. I am not expecting so, but again, it gives you an idea that this theory of radiation, what you read in your 10th, 12th, sorry, 12th physics book, is also there in the engineering, and that this significant create a significant challenges. You are designing a racing car, you want to minimize the temperature of the racing car in the combustion chamber. If the combustion chamber increases, there might be failure, right? So for this, although you will need someone who is specialized in radiation, but you primarily also you need to understand what is going on. And hope this theory will give you a detailed idea what this radiation and how it works. And it is quite challenging because all the mathematics you see in the things they are highly nonlinear in nature, right? And if someone thinks, okay, I'll directly do the experiment to design something, again, working with the radiation is quite hazardous. Okay, the only viable thing is the numerical or the simulation through which you can predict much of the things. Can you imagine you will do an experiment on a laser which is operating in the picosecond or femtosecond order and do the surgery with experiment? You need to understand this theory of radiation, right? And find the numerical prediction. One need to be a substantially good. One need a substantial good amount of knowledge in mathematics, physics, programming, all those things. Then only he can use it. Although there is some percent fluent star system available for us in industry to perform this task. But again, this is the whole concept of the radiation, whole theory of the radiation on which we are working. Further, I am not going to the subject because this, if I start the subject, in the whole semester course can be covered in this radiation heat transfer. But again, the radiation is a part, thermal radiation, especially the thermal radiation. Again, it is a heat transfer. So, like convection and conduction, it is a heat transfer mechanism. It's a long range phenomena. There is a mean free path. All those things are there. I am not going to cover further regarding the technical details of the radiation because people from the other side, other than mechanical, they may not find it interesting. But in this lecture, I have covered the entire scientific development of the total theory of radiation, right? So again, by doing so, a lot of things to study. Maybe some other forum we can clearly describe what is the surface to surface radiation. In mind, I like to close this lecture over here. So I like to acknowledge few of my mentors, guys. I especially Professor Surup Mahapatra, who is a man from radiation. I learned radiation from him during my PhD. There are few famous international authors like Michael Modest. I too have time to exchange few things from with him to get learn about radiation. Then Professor Subhash Mishra from IIT Guwahati, who is also a Indian genius of radiation, he did a lot of work from India. So I learned a lot of things from him. Then Professor Balaji from IIT Madras. These are few people I spent time in my academic career. I learned a lot of fantasy about radiation there. So in 2011, I was a PhD student. I was for some that time tsunami hit Japan and the Fukushima reactor was failed. Right. In that ISHMT conference, Professor Sumant Acharya and Professor Raj Mandit, who are professors from US, they are presenting some radiation model why this Fukushima this reactor is failing because they control the convection and the conduction heat transfer, but they are unable to prevent the radiative heat transfer. That's why the reactor was gradually going on failing, the nuclear reactor. So that time it was a quite fascinating topic in that meeting. So again, we substantially read on the subject matter, did some research from our end. But again, I like to thank all my professor, all my engineers who helped me to understand the thing and do research on the thing. Now, I close the session over here and open the session for the question answer. Sir, so can you move to question answer session? Hello? Hello? Hi, Samarjit sir.
Yes, sir. Yes, sir.
Can you unmute the students so that they can have any questions they can ask me? I can take any question from the next time.
So there is one question I am seeing in the chat box. What is the future of radiation?
Okay, future of radiation. Okay, radiation is already a 500-year-old concept as you see from atomic theory today in this the theory, as I explained. So the role and challenge of engineer to design a device, just like told, I met with Professor Kunal Mitra from Florida State University, who has his team was in the process of designing a device that will do the brain surgery without any through the radiation, means without any seizure or traditional surgery. They will put some laser. That laser is order of femtosecond. That will go. That will burn the entire tumor. Right. Similarly, such things I found. I was working in the artificial laboratory, artificial organ laboratory in US. I found a lot of people that developing some radiation device for the cancer diagnostic, right? So the future of radiation, especially if you are combined with the thermal radiation, the future is there from the semiconductor industry. The future is there from the electronics cooling. Sometimes because of the radiation, your mobile phone gets heated, right? You talk for 30, 40, 1 hour in a mobile phone, which is getting heated, right? The substantial challenge for any cell phone manufacturer to minimize those temperatures. Otherwise, if heated, the apps started behaving abnormally, the temperature, sorry, some few phones get switched off. So how handle those things? Challenge for the engineer working in the semiconductor industry. Currently, I am working in the home appliance industry. So for a challenge, just like we are doing the dryer simulation, that is to dry the cloth or the microwave, the home appliance we are using. How to provide an adequate temperature for the performance? It will dry the cloth, but at the same time, semiconductor component, electronics component will not melt down. Okay, so at that time, we have a significant role in reducing the radiation phenomena. We play with a lot of parameters over there to achieve those things. So this is where the future of the radiation I see, and further lot of things in radiation based device are coming in future, like laser and other things that will be affordable to common industry. They are also going to work on that. So that's my point of view. That is the future.
Thank you, sir. So one more question is, Any idea why cosmic background radiation that supports Big Bang theory lies in microwave region?
Very big question. I think you are asking a question to a wrong person. Maybe a physicist can answer this question clearly. My domain of working is clearly lies in the thermal radiation there. I can so it will not be justified for me to give some vague answer even if I am not confirmed. So I will take that question. I will if I get the answer, I will get back to you. But again, this is a nice question and I appreciate the question. I will answer back to you.
Any other questions from anyone if you want to ask something?
Sir, I want to ask a question.
Yeah,
Sure,
sure.
please go ahead.
We use microwaves to like cook things and heat up things. And there's that equation E is equals to h nu that proves like energy is directly proportional to frequency. So
What is
can
it? Yeah,
the visible spectrum lights be used like microwaves like to heat up things? I don't see any application as such because they are high energy waves.
that's why I explained the Planck's. There is a Rayleigh's law, there is a Wien's law. What will happen is new frequency. Half of the black body radiation, the Rayleigh's law was able to explain. Half of the radiation was explained by Wien's law. When Planck's mechanics E is equal to h nu, this is valid for all range of frequency. Why not for microwave region? There is
Yeah, yes, sir. That's why, like all waves of frequency are, we can apply the law, right?
yes.
So, like, can we use like for say violet light, which is high frequency as compared to like microwaves, to heat up things, and why those lights are not applied there? Like, why those frequencies are not used instead of microwaves? That would be easier, I guess. Like, the energy of those waves are like high, right?
Okay. So, do you think your home appliance like microwave you are using in a home? So, do you like to get cancer because you will use some high frequency phenomena which are a health hazard? Normally, the radiation frequency range that is close in the vicinity of range of the visible radiation that is not that much of harmful. Even if you go this either this side or that side, you'll get a enormous health hazard. So, do you want to use a microwave in your home? It will give you skin cancer. So
No,
for
sir. I'm not going to ultraviolet rays. Like, let's say blue light. Blue light. Why can't we use blue light instead of microwaves?
pardon?
Like, let's say blue light. Let's not go to ultraviolet light. Blue light has a higher frequency, so it has higher energy as compared to microwaves, which has very low frequency. So
Uh,
why is not blue light used instead of microwaves?
so the thing, the thermal radiation band entire all the spectrum of the radiation we are using instead a single source of radiation because economically and practically it is difficult to form a coherent source of radiation, right? So that's why the entire range we are using, the thermal range, we are using from the visible to the infrared region and for doing the thing. The microwave region is just above the infrared region. It can be used in microwave region. Why there is a problem? Is nu is higher, right? For microwave region.
Yes, sir.
Then what is the problem?
Yeah, like I don't see much of application of higher frequency
The,
wavelengths in
the,
day-to-day
the,
life.
the microwave has a frequency to 12 hertz almost, right? With this thing, we can generate a cooked food, microwave, right? Basically, this is the thermal infrared and microwave region where we are putting this some drive.
Yes, sir. Okay, I get it.
Obviously, we can go to ultraviolet, gamma rays, X-rays, those regions, the low frequency region, where because again, going to those regions may gives the hazard. They have the high frequency, but they are giving the hazard. And second, Wien's displacement law, you have seen the thing, it's not like the Wien's displacement law is not totally valid. There is a particular, at a particular temperature, particular wavelength range that gives the maximum radiation, right? So we have to take into mind. We cannot shift our for a particular temperature, we cannot shift our wavelength range such a region that we will miss the peak wavelength region, right? To keeping in thing,
Yes, sir.
all the range 10 to minus 1 to 10 to 2, all that micron range radiation we are considering. That is the thermal radiation range, right? Part of visible. And
Okay, sir. Yes, sir.
we are going to the microwave region. Most of the heat they go in the microwave region.
Yes, sir. Thank you, sir.
Yes, yes, welcome. Much development is needed, I think, in that basis. Yes, we need a much more enthusiastic scientist, much more enthusiastic engineer to do the development in this field. So, to be honest, in my entire PhD duration, I have seen people who quit the professor because they are afraid of the radiative heat transfer. I don't want to take the name. Most of the people they quit their PhD because they were assigned some radiation problem, and the mathematics and the phenomena is such complex that within few months they quit the thing because people have a difficulty in complex thing mathematics to understand those radiation, and we need much more brilliant mind to understand it and do the thing. Any more questions?
So there is one question: how feasible today's radiotherapy to the people?
Yeah, it's radiotherapy is feasible, right? Today's date in most of the medical school in USA, I have found people with cancer. They are undergoing radiotherapy. This radiotherapy is in practice. Come on, you are on seat. You are an enthusiastic engineering student. So why don't you ask questions? The only way to learn the field is to ask more and more questions.
Sir, I think students are not that explored to that radiation theory nowadays.
Yeah, I guess from the 12th level knowledge, I am not, while preparing the lecture, I assume that people are coming from the 12th after completing the 12th. So at least from the, what is there in the 12th, the cannot be with this minimal definition that the line displacement law, those things I put over here. A bare minimum requirement I put in the engineering. Yeah, definitely it will be a very new field to them as an exclusive radiation. But again, after few years after, once they are in a senior graduate like third year or fourth year, they study heat transfer. Those kind of or join the industry, join PhD. That time they can come to know about the essence of learning radiation. In Ottoman filling, size of the man get reduced. We are expecting better scope in that. I can properly get the question in the Ant-Man films. Man get reduced. Sorry, I am not aware about the things you are telling Ant-Man films. Is it a movie or something? Is it possible to reduce the size of a man? Maybe genetic engineer can answer it, the question. Hi Vikas, my question, why you want to reduce size of a man? You don't like tall man or what?
सर उस मूवी में साइज छोटा किया गया था आई मीन वही से ही तो मैं वही क्यूरियस था जानने के लिए कि क्या किसी आदमी का जो साइज है वो छोटा किया जा सकता है
Maybe genetically modify हो सकता है. I am not the proper person to answer those questions. Maybe if you can do some gene therapy, that can be helpful, and through radiation they do it. I heard it.
Yes, sir.
Yeah, because the short wavelength, right? They possess that much of energy. Once you put into the this DNA, they substantially modify the DNA, right? So in the process, if you directly find the radiation frequency that is going and repairing DNA, sometimes this study is going on, although it is not officially legal. But I heard few people they debate that this kind of thing is going on to alter the gene of this rat or mice. They put some radiation to try to modify those things. By that thing, suppose someone has genetic disorder and all. So by putting the radiation, they are trying to eliminate those things. But again, there is a positive side, negative side. If someone uses radiation to modify all the genes that has good aspect, that is the good aspect, then you are done.
yes sir. yes sir.
Yeah, basically they use the radiation to modify the DNA. That much of energy, once they come and hit your DNA, it will be by default modified, the composition. Biologically fantasy till now. Yeah, it's still in movie because in 19th century, if someone tell about the femtosecond laser and surgery in the brain surgery in the laser, maybe it looks like a movie, but today that it is going to be reality. So today it may be gene modification, maybe a fantasy for today, maybe next century it is going to happen reality. Who knows? That depends upon the development of the theory, development of the science. Any more question, guys? If not radiation, any okay, come out of the radiation. Any question about as a whole engineering or the project? Come on, it's an interaction session. Feel free to ask a question. I am not a teacher. Don't afraid of me. I am a friend.
So probably because of the long day, they might have drained out.
Yeah, it's the end of the day. They might be getting exhausted after a long session and all. So,
anyways, so Dr. Soham Kumar Jena is a very good friend of Dr. Sudhanshu. So who is a professor in
yeah,
mechanical engineering.
just a second, sir. Just a second. Some question from, I found that picture of the scientists sitting together and discussing about the experiment. Yeah, it something looks like the Instagram, right? I have the Instagram contact with scientists. Some people comments while you are putting some result or some formula, while you are putting the picture of the scientist. I told them my Instagram friends. So this is maybe addiction to Instagram. Joking. Okay, sir. If there is no more question, we can come to the end point.
Yes, sir. So thank you so much, sir, for this wonderful session and sharing your valuable thoughts to our young generation students. So probably they would have listened to you and learned something from today. And particularly for the mechanical engineers, Dr. Somkar Junna is a go-to person. Once you complete your BTech, you might again try to connect to him for your career in radiation field. So he has a vast experience and he has guided his career in mechanical engineering field in a very good way. So currently he is working as a CFD expert in Whirlpool Technology, Pune. So thank you so much, sir, and thank you, sir, for your time. And we can plan some deep technical session for our higher semester students. That will probably be engaging, more engaging from both the sides. So because of the lack of technical expertise for the audience today, maybe they will appreciate it once they are in higher semesters.
Yes, I understand the thing. So, in fact, it's a pleasure for me to join and interact with the young and dynamic mind. So, especially the question, I was never expecting something from the astronomical background. So, again, it's a really I'm happy that I have get a scope and interacted with so much of students. So, that's the beauty of being in academics. You will never get old. Every day, if you interact with this young and dynamic mind, you will stay young forever.
Yes, sir, that is correct. uh, Sir, we'll send you the recordings and all those things by email.
Can you please share me the recording? I like to wish everyone a happy engineering life, all the students. So you are in a best institution of the Orissa. So learn with the passion engineering. That's what I can advise our parents. Engineering is very, very interesting. Once you find the passion for it, you will enjoy the whole 4 years of your life. I wish all the best, and my best wishes are with you. With this, I like to also thank the board members of the city who organizing committee, Sudhanshu sir and Samarjit sir, for coordinating with me to make this session. So we can call up the session. Thanks everyone. Thanks for your patience to
Same to
listen
you.
to this
Thank you.
technical
Thank you, sir.
session. Thank you, sir. Thank you. Bye bye.
Bye bye, sir. So hello everyone. How are the sessions going?